So hi and hello there, welcome to the new video of the course, and in this particular video we are going to see a new concept, that is concept of dynamic resistance. Okay, so before coming to this particular topic, let me explain you these two particular terms. The very first term is static. static Static. So whenever you will listen to this particular term, so only one thing should come in your mind, that is something that is stable, right? Something that is stable. So the best example is, I hope that you might have heard about the example of comb and pieces of paper. Like whenever you will rub your comb on your hair, and if you are if you are placing it just near to that particular piece of paper, obviously that piece of paper will be getting attracted to the comb, right? So in that particular concept we talk about the static charge. Okay, so that means what? It's charges acquired by that particular comb, it is static. That means what? It is stable or it is constant, and that is present in that particular comb, right? Okay, I hope you understood this particular scenario. And if I'm talking about this particular term dynamic, so obviously now you can easily guess that dynamic can be opposite of static. So dynamic is something that is unstable, right? But over here the concept is talking about the dynamic resistance, right? So let me write over here, the concept is talking about dynamic dynamic resistance, right? That means what? The value of resistance is changing, right? That means it is talking about the, just a second, that means what? The value of resistance is changing, or in short what we can say is that this particular resistance is unstable, right? Just a second, this particular resistance is unstable. What you can say that, just a second, what I will do, I'll highlight it properly. Okay, this is a dynamic resistance, and what it states that unstable resistance, right? Unstable resistance. This is what we can conclude as of now. Okay, but now we all know that, see, we all know, let's suppose if this is a resistor, right? If this is a resistor, if it is 10 kilo ohms of resistor, if it is a 10 kilo ohms of resistor, right? We all know we cannot change its value. Obviously we can do that with, just by changing the area and length, but in reality we being a student, or we being a teacher, we cannot do it, right? Because there is some internal what I can say, conductor present in this particular resistor, right? We all know that R is equivalent to rho L by A, right? So based on this particular property, what we can do, we can increase the length, we can decrease the area, or we can decrease the length, or we can increase the area. Obviously we can do, but this can be done in some professional lab where where the resistor is produced, right? But as a student we cannot change it from we cannot change it externally, right? Okay, so that's the drawback. That means what? In reality we cannot change the value of the resistor. Okay, in reality we cannot change the value of this particular resistor, right? Just a second, in reality we cannot change the value of this resistor externally, right? Externally. Okay, this can only be done during the production. Okay, when this is manufactured, right? I hope you are getting my point. Okay, great. Okay, so we understood two things. Dynamic resistance is something that is related to resistor, or dynamic is something that is unstable. So basically it is talking about the unstable resistor, right? That means our value of resistor is changing. Okay, but there is one more concept. Now you will tell me, or most of the guys who are very much well acquainted this particular with this particular concept, that is potentiometer or potentiometer. Now you will tell me that over here we can easily change the value of resistor, right? We can easily change the value of resistor. We can easily change the value of resistor by rotating the knob, right? By rotating the knob. Okay, we all know this particular concept, right? Okay, or maybe few of you, those who are very much well aware with this particular potentiometer, they know this particular thing. But my dear students, what we are doing, we are rotating the knob and then we are setting the resistance according to our desire, right? Okay, so basically we are changing, again we are changing the value externally, we are changing the value of this particular resistor externally. Okay, changing the value of this particular potentiometer externally. Okay, I hope you are getting my point. That means what, basically we are doing the same thing over here. In this particular scenario we were unable to do so, so we introduce potentiometer. Okay, but now see over here, we are dealing with diode, and this particular concept deals with diode. That means what, a dynamic resistance of diode. I hope you are getting my point. See, these two particular thing, that is potentiometer and resistor, these two are totally different topics. Okay, these two are totally different components, and dynamic resistance only deals with diode. So remember this particular concept very very clearly. Why I explain you these two particular things? So that you should know that in reality the value of resistor cannot be changed, yeah, but the value of potentiometer can be changed externally. Okay, but now since we are dealing with diode, so we are talking about the dynamic resistance of diode. Okay, we are not at all interested in this particular resistor. Okay, I hope you are getting my point. So we'll write further, just a second. Yeah, dynamic resistor or dynamic resistance is the concept that deals only with dynamic resistance. Dynamic resistance comes into picture, or that is or dynamic resistance is the concept used only in diode. Okay, this is a concept used only in diodes. Okay, only in diodes. Okay, only in diodes. Okay, so now we understood this particular thing, that we cannot change the value of resistance, or we cannot change the value of this particular resistor, right? We can change this particular value of potentiometer, but as of now we are dealing with diode, so these two particular concept, they are of no use, right? But see, we can change the value of resistance, or basically the value of resistance or the internal resistance of the diode may get changed or may get affected because of two factors. So now you will ask me, sir, what is that particular factor? We all know that V is equivalent to I into R, right? Okay, so for time being, what I will do, just a second, I'll write it in smaller way. Why? Because I need to explain you certain thing, and then I will explain in that why I'm writing with in some in the smaller alphabet. So this is equivalent to V is equivalent to I into R. Okay, we all know this particular thing. Okay, but now since we are dealing with diode, so what I will do, I'll just put this particular thing as VD relates with the diode voltage, ID relates with the diode current, and RD relates with the diode resistance, right? So therefore your RD is equivalent to VD by what? VD by ID. Okay, VD by ID. Okay, so just few minutes back we were unable to change the value of the resistance, okay, over here. But over here, what if I change the value of voltage, right? Let's suppose if I'm changing the value of voltage, right? Voltage, or if I'm fluctuating it, right? If I'm fluctuating, or if I'm changing the value of voltage, right? So obviously the value of current will also change, right? So what I will do, I'll just write in this way, of current. Okay, so that means what, we can change the value of resistance by changing the value of voltage and current. I hope you are getting my point. Just a second, let me highlight it, the help of one box. Okay, the help of one box. So that means what, basically we are providing unstable voltage and unstable current. I hope you are getting my point. Okay, over here static means what, something that is stable, right? But dynamic means what, something that is unstable. And since we are dealing with dynamic resistance, that means what, the resistance of the diode is unstable. I hope you are getting my point. That means what, we are providing AC voltage, or basically unstable voltage. Okay, and due to that unstable voltage, unstable current is generated. Okay, and thus the value of the resistance or the internal resistance of the diode, it is getting changed. Okay, And since we are introducing an AC voltage and current in the diode, so that's why we are dealing with the dynamic resistance. I hope you're able to understand this particular point. So now I will write the definition of this particular uh, dynamic resistance. I hope you understood this particular point. Okay, so dynamic resistance is the resistance, just a second, this would be a kind of definition for the dynamic resistance. Okay, so let me write over here dynamic resistance. Dynamic resistance is the resistance offered by the PN junction diode, or diode offered by the diode when AC voltage is applied, right? When AC voltage is applied, when AC voltage is applied. Great. So this is the fundamental definition of supplied of what? Dynamic resistance. And most of the students, they fail to understand this particular concept in depth. Okay, they don't know what is the dynamic resistance and why we are using it and all. Okay, so the actual meaning of the dynamic resistance is what? First of all, dynamic means what? We are introducing an AC voltage or AC current, and since we are introducing this AC voltage and AC current, so obviously there would be a change in voltage and current, and this particular change can be represented in this particular graph. See, as you can see over here, this particular change in current and change in voltage is represented in this particular graph, I versus V graph, or VI characteristics of diode, which we had seen in the previous session of the course. Okay, I hope you know this particular graph. Okay, great. Now you will tell me, sir, just a second, this particular AC voltage has two waveform. Okay, that is one positive half and one negative half. Okay, one positive half and one negative half. Okay, but diode has that property that it will reject this negative waveform. Why? Because any voltage less than 0, for ideal diode I am talking, it will reject this. Yes, that is absolutely correct. So it will reject this particular thing. But now you only think, see, I'm just talking about this particular waveform, the positive half cycle. I'll draw it over here properly, so that you should understand this particular concept in depth. Okay, let's suppose this is your, for time being we'll just take one graph. Okay, that is V versus T. So this is your voltage versus time graph. Just a second, let me select proper color. Yeah, so this is your voltage versus time graph, right? And this is your AC waveform. I'm only drawing the positive half of the AC waveform, right? Positive half of the AC waveform. Just a second, let me draw it properly. Yeah, something like this. All right, so as you can see over here very clearly, as your time is increasing, your voltage is also increasing. Okay, as your time is increasing, your voltage is also increasing. That means what? As your time increases, voltage increases, and as the voltage increases, right, V is directly proportional to I, so your I also increases. I hope you are getting my point. And therefore over here, that's why you see over here in AC, see over here the voltage, let me draw it over here, something like this. Your voltage is increasing with respect to time. Okay, this is what we see now, we saw now, sorry. Okay, this is your time, drawing it little roughly. This is your voltage, right? This is your positive waveform. This is your positive waveform, and as your voltage is changing, so your current is also changing with respect to time. I hope you are getting my point. Okay, and this particular change is represented with the help of this particular RD, or dynamic resistance. Okay, I hope now you understood this particular concept of dynamic resistance. Okay, and obviously this is the formula for dynamic resistance. RD is equivalent to del VD by del ID. But still things are not over yet, right? Still things are not over yet. So just a second, I will show over here. This is the positive voltage. I am showing it the help of DC voltage, so that you should understood this particular concept in depth. Okay, so this is your plus V, right? And this is your grounded. This is grounded, right? This is grounded. Great. This is your p type region, p type p type region, okay, and this is your n type region, n type n type region, n type region. Obviously yeah, hope you now you are in this particular scenario that what these two regions are made up of. It is made up of holes or lesser electrons, it is made up of more electrons, okay. And this is the depletion region. I'm not going in that detailed way because I had explained this particular concept earlier as well, okay. So this is the symbol of the p-n junction diode. So this is your p region and this is your n region, right? Great. And as we had seen in the previous video that in case of DC, I mean in case of DC analysis, or when we were supplying DC voltage, right, over here it is AC voltage. I will write over here this is your AC voltage, okay, so that you should not get confused. And yeah, just a second, I forgot to explain this particular thing, that why I'm taking this particular smaller alphabets. So whenever you write capital alphabets, P is equivalent to I into R. So generally traditionally it is known that whenever you are writing this particular capital alphabet, so it is used for DC analysis. DC analysis, I will write over here DC analysis, right? And whenever you are using this smaller alphabet, so it is known for AC analysis. That means you are dealing with AC analysis, okay. That's the simple reason, or that's simple logic. Traditionally it is used, okay, and that's why most of the colleges or most of the tutors they prefer using this particular thing, okay. I hope you understood it. As such, there isn't any logic. All right. So in case of DC analysis, what we saw was we were not including this particular resistor or dynamic resistance. We were not including this particular dynamic resistance. Why? Because in case of DC analysis, see, in case of DC analysis, the voltage was stable, right? The voltage was stable, and if the voltage is stable, so current is also stable. And if the current is stable, so obviously your V by I would also be stable, and that's why in case of DC analysis, we were not at all representing this particular dynamic resistance, or what I can say, the change in voltage del Vd by del Id. Over here I had written this particular formula, del Vd, change in voltage or change in current, was absent, or change in voltage over, I mean change in voltage divided by change in current was absent in case of DC voltage or DC analysis, okay, in case of DC analysis. But now since we are dealing with AC, this VAC indicates that we are dealing with AC voltage, okay, although AC voltage is shown in this way, but for your understanding purpose I'm not showing it in this way, okay, so that you should understand this particular concept in depth, okay. And yeah, so that's why since we are dealing with AC voltage, I had represented over here RD, or the dynamic resistance, okay. And this is how the graph will look like, okay, as we had seen in the previous sessions. This is the formula that we had derived just now, okay. This triangle sign is nothing but it is change, okay, small change in voltage with respect to current, right, okay. Sorry, small change in current with respect to this small change in voltage, okay. I hope you understood this particular concept. And we all know what is the value of current or the diode current, that is ID is equivalent to IS, that is saturation current, into E raised to Vd by Vt minus of 1. Vt is your thermal voltage, which was equivalent to which is equivalent to 26 millivolt, that we had seen in the previous session, I guess, if I'm not mistaken, right? So basically we had seen this particular formula in the previous session, okay. So what I will do, I need to derive certain things. So what I will do is, just a second, yeah. So we all know that see, we all know this particular formula. So what I'll do, I'll just extend this particular formula. ID is equivalent to IS into E raised to Vd by Vt minus of IS. So now if you could see this particular part, okay, this particular part, you can actually substitute this IS is equivalent to, almost equivalent to 0. Now you will ask me why, sir? Obviously IS is nothing but reverse saturation current. So whenever we will deal with a reverse saturation current, just a second, let me take certain different color, yeah, I'll take this one only. So I'm talking about this current, see, it would be almost equivalent to 0, and at some point if I'm exceeding the voltage, I mean negative voltage, so it would be, you know, this particular current would be as high as possible, right? So this is known as breakdown region of diode. I hope you know this particular concept. This is your, just a second, minus of Vd, this is your minus of Vd, and this particular current is known as IS, reverse saturation current. And as you can see, up to certain voltage, up to certain negative voltage, it is almost equivalent to zero. So that's why rather than taking taking the value of this particular current, which would be in very few, I think it would be in microampere, right? It would be in microampere. So remember one thing, in reality this particular current, it would be equivalent to maybe 1 or 2 or 3 microampere, something like that. It would be in microampere. So rather than taking this particular value, it's absolutely fine even if we take this particular value of current as 0. Okay, so that means what, we are left with this particular value, that is the value of current id, it is equivalent to, or the value of diode current, it is equivalent to is into e raised to vd by vt. Okay, vd by vt. I hope you understood this particular concept. So this is the formula for diode. Okay, this is the formula for diode. Okay, great. And now moving further, see, just a second. We all know the value for the dynamic resistance, and it was rd, just a second, rd was equivalent to del vd by del id. Okay, del vd by, oh sorry, since I'm dealing with ec, right, so I should write in small alphabets, del vd by del id, right, del vd by del id. Okay, so now I can also write in this way, d by, since we are dealing with very small change. Okay, so over here we would be, the AC voltage, it would be very small, right? It would be maybe a few millivolts or maybe a few volts, right? So we can also write in this way, d by this dvd by d id indicates that the change which has happened in the voltage and current, it is very small. Okay, so now we cannot differentiate vd with respect to id uh, vd is because we don't know the formula for vd. So what we can do over here is that we can write in this way, that is 1 by rd. 1 by rd, we can just take a reciprocal of it, right? 1 by rd, and then we can easily differentiate the further thing. 1 by rd is equivalent to did by dvd, right? And we all know the formula for id, so this is the formula for id. Great. So now we can easily substitute this particular formula over here. So this would be equivalent to d by dvd, just a second, d by dvd into bracket id, sorry, is into e raised to vd by vt, right? Great. So now, as you all know, is is constant, so it will come out of the bracket, so it would be is into d by dvd of vd of vd into bracket e raised to vd by vt. See, now I had written it in capital. Okay, so just to solve this particular mathematical equation. So now I hope you know the basic formula for differentiation, so I'm not explaining this particular part. So my 1 by rd would be equivalent to is into e vd by vt, okay, divided by 1 by vt, right? I hope you understood, or I hope you know how to solve this particular equation. Now I will not tell you how to solve this particular thing, because this is very basic mathematics. Okay, so thus what, thus my 1 by rd is equivalent to is into e vd by vt divided by vt. And now just a second, let me move this particular whole of this particular equation little below. Alright, so now if you look at this particular equation very clearly, maybe I will take yeah, this will do. So yeah, now if you look at this particular equation very clearly, you will get this one: is into e raised to vd by vt is was equivalent to id, right? So I can substitute this particular value as id itself, right? So my 1 by rd, sorry, yeah, so my 1 by rd, 1 by rd is equivalent to id by bt. So now what I will do, I will again take the reciprocal, or I can do cross multiplication. Okay, it's one and the same. So therefore the value of rd is equivalent to vt by id, vt by id. I hope you understood this particular concept. Okay, and the value of vt, just a second, this is the formula for rd, or the dynamic resistance, and the value of vt, first of all vt is the thermal voltage. So this is the thermal voltage, okay. I had explained you this particular concept in the previous session. So vt is vt is equivalent to 26 millivolts at room temperature, okay. And this is your diode current, id is your diode current, okay. So this is the formula for the dynamic resistance, okay. I hope you understood this particular concept in depth. If you have any doubts, feel free to ask me at any time. I will surely help you. So thank you for listening me patiently. I am ending this video over here. Thank you.